Hello guys, so welcome back to our second part of lecture 3. So in the first part of lecture 3, we explored the basic axioms and postulates, that we use in Boolean algebra. Okay, I'm showing you here all these postulates. Okay, they are very easy and we use, or very intuitive, we can say. Although we proved them, but we proved them using the definitions that we, the basic definitions of Boolean algebra, especially the truth table. And basically, the only proof of them are actually the truth table. Okay, it was easy to drive all of them because we have at most 3 variables. Okay, in this part, we're gonna explore the basic theorems now that basically based on these postulates that we discovered or explored. Okay, let's start by these theorems can be proved using 2 types now. They can be proved in algebraic form or using the truth table, just like the postulates. Okay. Okay, so let's start by theorem 1 here, which is x or x equal to x, x and x equal to x. Okay, basically, if you have an OR gate like this, and it has basically OR gate has 2 inputs, but if we just short the 2 inputs together, we'll get the same input in the output, same as for the AND gate. Just to to imagine the situation here. Okay, so basically we can prove them using truth table in algebraic form. So let's start by the truth table. So the truth table here, we have only one variable x, can be either 0 or 1, because this is Boolean variable, just 1 bit. Okay, so we have 2 choices, 2 options, either 0 or 1. And in the first part here, we're gonna theorem 1a, we're gonna OR it with itself. So again, 0 and 1. Okay, so 0 or 0 is 0, 1 or 1 is 1. This is x or x. And if we just compare 0, 1, 0, 1, so basically this is equal to x. And if we try to prove x dot x equal to x, or x and x equal to x, using truth table, we have the same stuff, x, 0, 1, 0, 1, here is x dot x. Okay, so 0 and 0 is 0, 1 and 1 is 1. Maybe some will ask, we have here 2 variables, not 1. No, it's 1 variable. Okay, you can't have the combinations. You can't say that x and x is 2 columns, each one of them is x. Then you say 0, 0, 0, 1, 1, 0, 1, 1. No, you can't say this, because basically this is x and x, so they should be equal. So you can't have the situation in which you have x equal to 0 at the same time x equal to 1. Okay. Okay, this is the proof by a truth table, which is really easy, as you see here. Okay. Now, how to prove them in algebraic form? Okay. So let's start by x or x equal to x. So we have here, the left-hand side. Here is the right-hand side. And we should prove it. So we should prove that. Okay. So let's try to do that. Okay, let's start by the left-hand side. So for the left-hand side here, x or x. What we have? We have only the axioms, the postulates. Okay, so we should look here and try to find, somehow to reach from the left-hand side to the right-hand side, x. We know that if we AND anything with 1, it will give us the same stuff, which is postulate 2p. So we're gonna here AND x or x with 1. So this is postulate 2b. Good. And we know that x or x bar equal to 1. So we can replace this one here by postulate 5a, which is x or x bar. So this will lead us to x or x, no change. But this one we will substitute it with x or x bar. This is postulate 5a. Okay. Now let's look at the distributive property or the distributive postulate. This one, this two. Okay, we're gonna use one of them now. So this actually is very similar to this guy, right? Which is postulate for B, in which we distribute x over y and z. Okay. So basically what we have here is the output. So this is, you know, analogous to this one. Okay, the common factor here is x. And the two variables, which y and z in that case, postulate to b, is actually x and x bar. Okay, so this is basically equal to x or x and x bar. This is from postulate 4b. Good. Now x and x bar. If we look again here at postulate 5b, x and x bar is equal to 0. So this is actually equal to 0. So x plus or x and x bar is actually equal to 0. This is postulate 5b. Then finally, x or 0 from postulate 2a. From postulate 2a. Okay, so we used in each step most of the postulates that we discussed. Okay, basically that's what we have. So we started by definitions. Okay, some the definition has no proof. You know, this is a definition. This is the basics that you put. It has no proof. Then one of these definitions was the truth table. You know, one of the tools that we define. And this truth table has a property that it gathers all the space or all the possible values for a function. Okay, and its inputs. Using this truth table, we could prove all the postulates. Then using the postulates, we can prove theorems, you know, what comes next, which is theorems. And actually theorems can use both the definitions, so it can be proved using the truth table, or, you know, the postulates that we prove based on the truth table. Okay, we did both here. So let's prove, you know, x dot x equal to x. So I'm gonna change the color. Let's use, for example, this blue here. Okay, it's very similar, but we're gonna use 0, not 1. So x. So again, this is left hand side. This is the right hand side, and we want to reach the right hand side from the left hand side. So x dot x. If we OR 0 using postulate 2a, it will give us the same stuff. So we will not change our term here if we OR 0. This is from postulate 2a. Okay. And if we look to postulate 5b, 0 is actually x and x bar. So this is equal to x and x again, no change, and 0 is x and x bar. This is postulate 5b. Very nice. Then we look at the distributive, right? We have here something similar to this postulate 4a. Okay, so basically here, this is similar to the left-hand side, the right-hand side, I'm sorry, which is x dot y or x and z. Okay, so basically x here is x, and here is the common factor. I mean, And then y and z, this is y, this is analogous to y, this is analogous to x, z. Okay, so basically this can be written as x dot y or z, and y here is x, and the other one z is x bar. This is from postulate 4a. Okay, 4a. Good. Then if we look at postulate 5a, this one here, x or x bar is 1. So this is x dot or and 1 from postulate 5a. And finally, if we look at postulate 2b, okay, 1 dot anything, you know, or 1 and anything is the same stuff. Same thing, I mean, x. So this will give us x from postulate 2b. Okay. So again, this is very neat, you know. You have both options table or the postulates that you have. I know it's very intuitive. We all the time use x dot x equal to x, you know, as granted. Okay, but it has a proof, and here is a proof. Here is actually the two proofs using truth table or the postulates that of Boolean algebra. Okay, let's go to another theorem. X or 1 equal to 1, and x dot 0 is equal to 0. Also, these are taken for granted. Okay, but we're gonna prove them now. Let's start by the truth table. Let's change the color again to red. Let's start by the truth table. So here is x, 0 and 1, and here is the 1, you know, it's always 1 constant. It's not a variable. So this x or 1. X or 1, 0 or 1 is 1, 1 or 1 is 1. So whatever x, the output is constant equal to 1. This is the proof. Then x dot 0 equal to 0, so x 0, 1, and here is always 0, and here is x and 0. 0 or 0 is 0, 1 or 0 is 0 again. So whatever x, if you end it with 0, it will give you 0. So again, here we prove the second. So let's prove them algebraically, you know, using the postulates or the axioms that we have. So let's continue with red. X or 1 equal to 1. Again, this is the left-hand side, right-hand side. And we want to go to the right-hand side from the left-hand side. So x or 1 is very similar to the, you know, the previous proof. You know, you're gonna end also with 1 here. And we know ending with 1 will give us the same stuff. Okay, this is postulate 2b. This is postulate 2b. And actually 1 is x or x bar. So x or 1, x or x bar. So we can remove this one and put x or x bar. This is postulate 5a. And this is again the distributive. So same sequence. So for the distributive here, this is similar to 4b. Okay, so we have here, this is x, the common factor, and y is analogous to what? 1 is analogous to y, and x bar is analogous to z. Okay, so basically this can be simplified to x or 1 dot x bar. 1 dot x bar. Okay. And what is 1 dot x bar? If we look at, you know, postulate 2b, or this is from postulate 4b. 1 dot x bar, anything ended with 1 give you the same stuff. This is from postulate 2b. So this actually x bar. So this is x plus x bar or x bar. This is postulate 2b. And finally, x or x bar, if we look here at postulate 5a, this is actually equal to 1. So this is equal to 1 from postulate 5a. Okay, and that's it. No, that's the end of it. what we want to prove. Okay, let's now prove the second one. X dot 0 equal to 0, x and 0 equal to 0, whatever the value of x. Okay, so let's start. Let's do it. It will be again similar to what we have seen for that proof here. Let's show it again. This one. We again would or 0 this time. So x dot 0. This is the left hand side. We want to reach the right hand side from the left hand side. Okay. So basically, what we're gonna do, as I said, we're gonna OR 0. So we're gonna OR 0 here. This is will not change anything, and this is from postulate 2a. That anything ORed with 0 will give you the same stuff. Good. Now 0 is x and x bar. So x dot 0 plus or x dot x bar. Postulate 5b. Again, the derivative property. This is similar to this one, this component here. 0 is analogous to y and x bar is analogous to z. This can be simplified to x dot y or z, 0 or x bar. Postulate 4a. Then 0 or anything will give you the same stuff. Postulate 2a. So this will give us x bar. So x dot x bar. Postulate 2a. Okay, and finally, anything ended with its complement will give you 0. So x dot x bar here from postulate 5b is 0. So this is equal to 0 from postulate 5b. Okay, so this is basically the first two theorems. Okay, and let's now continue with other ones. Yeah, we're gonna start by theorem 6 because theorem 3 and 4 and 5 are hard to prove in algebra. It's very long. Okay, not hard, but very long. Okay, so I'm gonna do them by using the truth table. And actually they use the theorem. So whenever you prove a theorem, you can use it in another theorem. Okay, so basically each theorem you prove, you can use it later in other theorems. Okay, and this is what happened. So one of the theorems, DeMorgan's theorem, depend on this theorem, theorem 6, in its proof in algebra 4. Okay, good. So let's do theorem 6 here. Okay, using truth table, it's really simple. Again, you have here to, of course, x or x dot y or and y is equal to x. And this is called the absorption. Y is absorbed, or is this term x dot y is absorbed actually in x. Okay, and x dot x or y is equal to x. Again, this term x or y is absorbed, or y as a second variable is absorbed. So it's like if you have only one variable, the second one has no effect, we can say. Okay, so basically you have here two variables x and y, and you have two sides, right hand side and left hand side. So let's start by the first one here. We need to prove that x or x dot y is equal to x. Okay, so here is x and y, 4 combinations, 0 0 0 1 1 0 1 1. Here is x dot y. We need this one here. X dot y 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Good. Now we OR x dot y term with x. So if we OR this guy with this, it will give us 0 0 1 1. If we compare this now with this, they are equal. They are equal. Okay. So this is basically, the proof of the first one. So this is the proof, the truth table proof. For theorem 2a. and we should do to be similarly. It's very simple. Okay. But what's interesting here is to prove them algebraically. Okay, so let's do that. Again, we do the same stuff. We look at the postulates or axioms that we have and try to deduce or derive, or prove that the left-hand side is equal to right-hand side. So let's start by the left-hand side, x or x dot y. Okay, good. So, same trick. Each time we either or 0 or and 1. Okay, but now we should choose which term, because we have terms here, x and the other term is x dot y. And actually, we're gonna dot 1 or and 1 with x. So this is basically equal to x dot 1 or x dot y. Nothing changed because x dot anything, 1 dot anything will give you the same stuff. So x dot 1 is actually equal to x. We will not change. This is postulate 2b. So this is postulate 2b. Good. Okay. Now, if we look here, this is again the distributive property, the distributive axiom. Okay. So this is similar to this one, the left-hand side actually. So we have here x is a common factor, and y is analogous to 1, and z is analogous to y, or whatever, y is analogous to y, and z analogous to 1. It doesn't change. Okay, so this can be simplified to x dot 1 or y. Okay, like this one, 1 or y. This is postulate 4a. And now 1 or y. Okay, if you remember that in theorem 2, let's review it. In theorem 2, x or y, or I'm sorry, x or 1 is equal to 1. Anything ORed with 1 will give you 1. Okay, so we're gonna use this theorem now. And again, as I said, theorems can lead to other theorems. Okay, so we should use what you get. We proved the theorem 2 that x or 1 is equal to 1, so we can use it in other theorems. So that's the case here. So in theorem 6, okay, we have this 1 or y. So from theorem 2 to a, this is actually equal to x dot 1. This is equal to 1. 1 or y is equal to 1 from theorem 2a. And now if we look at the postulates now, from postulate 2, 1 dot x is equal to x. That's the case here. So this is equal to x. This is postulate 2b. So yeah, we proved it, that x or x dot y, which is really weird, equal to x, because y just vanished. Okay, y is just vanished. Again, most of these beautiful properties, comes from the fact that these are Boolean operators, Boolean variables that either 0 or 1. And 0 or 1 in arithmetic, they are really two numbers with very huge, properties, distinctive properties. Like, for example, if you add 1 with anything, if you add 0 with anything, it gives you the same stuff. If you multiply 1, like ending in our case here, will give you the same stuff. Okay, that's why there are there are flexibility, we can say, in using these Boolean operators. Okay, let's now prove the second theorem here, x dot x or y equal to x, just like again y is vanished. So let's do it in another color. Let's go to red here. Okay, x dot x or y equal to x. Here we ended 1 with x, here we or 0 with x. So x or 0 dot x or y. This is the left-hand side, and I just ORed 0 with x, the first term in the left-hand side. And this has no effect, basically, because when you OR anything with 0, it will give you the same variable. Okay, this is postulate 2a. Okay, then the distributive property. This is actually similar to, postulate 4b, and it can be simplified to, this is the common factor x. This can be simplified to x or 0 and y. Postulate 4b. And again, we're gonna use one of the theorems that we proved. Okay, so if we go back here to theorem 2, to be 0 dot or ended with any variable will give you 0. So this is our case here. 0 ended with any variable will give you 0. So this is actually equal to x or 0. This is from theorem 2b, not postulate, theorem. Okay. Now x or 0 give you x. So this is actually equal to x. Why? Because we have, postulate 2a here. This is very nice because now we used, the definitions that you define for Boolean algebra, like the truth table, and you could prove it these two axioms. Theorems using the truth table, and you could also prove them algebraically using, postulates and also other theorems that you discovered, before that. Okay. Now we go to theorem 4 and 5, which is distributive, and DeMorgan, theorem 5 after this. Okay, and the best way here is to do the truth table. The proofs are really long, so we're gonna use the truth table. Okay. So I leave this for you as a homework to do, to do the proof, but it will be very similar to that one. So we did something very similar last time in lecture 1A, we can say, the first part of this lecture, which is this one, postulate 4A and 4B. Okay, that's derivative. We did something very similar to it. So basically, you're gonna, calculate y or z, then OR it with x. Okay, in a column, then you OR x and y and OR it with z in another column. Then you compare the two columns. They should be equal, and the same for this one. Okay. For DeMorgan's theorem 5, which is called DeMorgan theorem. DeMorgan is the guy that discovered this or proved the theorem, which is really nice as well, and we're gonna use it a lot. Okay. That if you OR two variables together, then you take the inverter or the complement for the result. It will be equivalent to AND the two complement of these two variables. So here, this is for theorem 5a, for example. Here you OR x and y, then you take the complement. It's very similar if you take the ending of x complement and y complement. What happened here is that you convert the OR into AND and distribute the complement on the x and y. Okay. Same if you have x dot y complement. I mean, your complement is a result of x and y. It's like if you make the OR between the two complements of the two variables. Again, you convert the dot or the AND into OR, and the complement is distributed between the two variables, x, y, and z. Okay. And this is basically can be done for more than two variables. So let's say we have z. So x or y or z complement for the whole. This is actually equal to, just to convert the OR into AND x dot y dot z and distribute the the bar, the complement over all the variables. Okay, and similarly, x and y and z with complement is x or y or z and distribute the complement. And you can do that for 4 variables, 5 variables, whatever. Okay. Again, the proof is long in algebraic find. We're gonna use a lot of the theorems, especially the theorem 6, which is this one, the absorption theorem. Okay, and of course some postulates. So basically, we're gonna use here it's easier, a lot easier to use the definitions, the truth table. Okay. So for example, here, let's prove the first one, theorem 5a. So this is a proof for 5a, theorem 5a. Okay. We wanna prove that the right hand side equal to the left hand side. So this is the left hand side, x or y complement. So we first do the x or y. Here is x and y, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Then you take the complement of that, it will give you 1, 0, 0, 0. Then the right hand side. So the right hand side, we need x complement and y complement. Here is x complement and here is y complement. You just take the complement of that. So we started this by 2 zeros into 1s. Here is 2 1s and 2 zeros. Here we start with 0, 1, 0, 0, 1, 0, 1. Here is 1, 0, 1, 0. Then you take the ending. 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0. If you just compare this column by this column, they are equal. So you could prove theorem 5a, and similarly you can prove theorem 5b. Okay, guys. So let's now review all the theorems in that table. Okay. So here all the postulates, all the theorems that we discussed so far. Okay, we proved the postulate or the axioms using the truth table. We proved the theorems using the truth table. We can do that using truth table. We can use the axioms or the postulates, and also you can use other proved theorems, like what we have done, for example, when we do theorem 6, the absorption, this one. Where is it? This one, yes. In which we use 2a and 2b. Okay. One note here, is that if you look at all the postulates and the theorem, you see a kind of duality between all the a's here and all the b's. Each postulate has a and b. Each theorem has also a and b. Okay. So we could prove that x or 0 equal to x and x dot 1 equal to x. For postulate 2, for example. For postulate 5, x or x bar equal to 1, x dot x prime or bar equal to 0. Okay, and so on. So this is a very famous duality called the duality principle in Boolean algebra. Okay, in which if we just hide this part here, and we could prove only the a part, all the postulate and theorem of a, just by changing the 0 into 1, or the 1 into 0, or into and, or dot, you can get number b. So let's do that. For example, we're gonna don't look at b, just do it using these principles, the duality principle. So we're gonna convert any or into and. So x will not be converted. The or will be converted into and. The 0 will be converted into 1. X has no change. So x dot 1 is equal to x. That's exactly what we have here. Let's pick anything. So let's do, for example, the associative. Just convert so x, y, and z. This should have no change. X, Y, and Z should have no change. Then convert all the ORs into ANDs. Then do the brackets. If we look here, that's exactly what we have. Sorry. Yeah, that's exactly what we have. X dot Y and Z equal to X and Y between brackets, then and Z. Okay. Let's do, for example, last example is absorption. X and X or Y. This should be X. If we look here, that's exactly what we did in B. Okay, this is very famous and very useful property, this duality principle. Okay, so guys, we discovered or we explored now basic definitions of Boolean algebra, basic theorem axioms or postulates in Boolean algebra, and from these postulates or axioms, we did prove other useful properties, which are the theorems that are summarized here in that table. Okay, so in the next video we're gonna explore the basic how the basic function definition in Boolean algebra, how to construct a function, okay, and what are the main property in function in Boolean algebra. So see you next time.